Hello, and thank you for joining. My name is Derek Kane, and today we're going to get into the topic of big data fundamentals for data scientists. This presentation is just one lecture in a broader series of lectures diving into topics of predictive analytics, machine learning, statistics, and data science. If you like this content, please feel free to check out some of my other videos and make sure you subscribe to the channel. Okay, let's go ahead and begin. The overview of topics that we're going to get into today are going to first start off with a preface to the lecture in general. Then we'll shift and we'll get into the history of the big data and talk about why it's important. Afterwards, we will shift focus and we will start diving into a little more detail about the big data ecosystem. And there are a lot of different technologies that drive the big data environment, and we're going to try to touch upon some of the major ones. Then we will look at utilizing big data with the R programming language. And finally, we will tie this all together in a practical application example, where we'll go through an exercise of taxicab analytics in R that draw from big data concepts. The big data space is truly the Wild West of analytics and one of the pinnacle achievements of the modern information era. As such, the landscape is rapidly evolving, and software vendors are each offering their own implementations of the core technologies that drive big data. There are a lot of different technologies and options the data scientists have to choose from, and can be quite daunting when deciding on a platform. Furthermore, business leaders are relying on our expertise when deciding the big data ecosystem to set up for the end-to-end analytics spectrum. The intention of this lecture is to provide awareness of the underlying techniques of working with big data technologies from a data scientist's perspective, exploring big data machine learning with R. With a functional understanding of the mechanics of big data techniques, data science professionals will be poised to be able to deploy the analytical techniques regardless of the hardware-software technologies deployed. We will spend some time going over some of the notable pioneering technologies from the Apache Software Foundation and their IT underpinnings. And I think this is an important point to bring up because we're really going to dive into some detail here, and there are a lot of different technologies and they are quite complex. But the emphasis here is to understand the mechanics of the big data process, and as such, we're going to focus on the Apache Software Foundation and the R language. However, a proper evaluation needs to be made with the CIO and aligned to the organization's analytical goals when selecting the appropriate software hardware deployment. This is a critical piece because when people hear about big data environments and jumping on the bandwagon, if you will, what exactly does that mean? How does this impact the organization? How does it benefit the organization? And hopefully, after going through this lecture, we should at least have a functional understanding and be able to answer some of those questions. And I think a key point to drive is that not all big data projects require the complete ecosystem. There's going to be a lot of complex aspects that are going to be thrown to you throughout this lecture, but just understand that just because you're advancing a big data project doesn't mean you need all of the technologies to support it. For example, Walmart will have different storage and analytical needs than Google's YouTube business. An interesting fact, Walmart handles more than 1 million customer transactions every hour, which is imported into databases estimated to contain more than 2.5 petabytes of data, which is the rough equivalent of 167 times the information contained in all of the books in the US Library of Congress. But the big data needs of what it takes to drive a YouTube business, a video streaming business, is different than a brick and mortar Walmart business or operating in a retail environment or hybrid brick and mortar environment. So then this begs the question, which technologies do you actually need to navigate this exciting new landscape? Just to show you how complex this is, let's just look at this graphic here that shows the landscape of technologies in 2012. I'm not going to get into all the technologies, but as you can see, there's a fair amount of them. Well, here is a more current iteration of the landscape. Are you getting a little more nervous? Well, don't worry. We will sift through the noise and get to the heart of big data. My intention in this lecture is to take the noise of this landscape, all these technologies and vendors, and just boil it down to the essence of working with the data as a data science professional. But as you can clearly see, there are a lot of players operating in this space. So one of my favorite cartoons is this Dilbert cartoon talking about big data, and it's basically just saying that consultants are telling you that, hey, there's all this data being generated across the globe. We gotta tap into that data, and if we don't jump on it now, we're going to be in big trouble. So this is just making light of the whole big data movement, I find it to be a very funny cartoon. Well, there's a data explosion in the 21st century. Developed economies make increasingly use of data-intensive technologies. There are 4.6 billion mobile phone subscriptions worldwide, and there are between 1 billion and 2 billion people accessing the internet. Between 1990 and 2005, more than 1 billion people worldwide entered the middle class, which means more and more people who gain money will become more literate, which in turn leads to information growth. In my first lecture, I spent a fair amount of time going over this particular graphic and discussing the big data era. This is a particularly useful graphic, and it kind of showcases the transition of analog moving into a more digital domain in terms of the type of data that is being stored and utilized. And we can actually see that as we move forward in time, that digital storage begins to overtake analog storage, and then we have an explosion starting in 2002. So if you're interested in a more thorough analysis, please feel free to check out the Predictive Capabilities lecture. In 2007, the amount of digital data represents about 61 CDs worth of information for every human on the planet. If we were to stack these 404 billion CDs on top of one another, this stack would reach the moon and a quarter of the distance beyond. According to Cisco IP traffic forecast, global mobile data traffic will grow 131% between 2008 and 2013, reaching 2 exabytes per month in 2013. A single exabyte is roughly equivalent to the entire US Library of Congress text duplicated 100,000 times. By the end of 2016, annual global traffic will reach 1.3 zettabytes or 110.3 exabytes per month. So the amount of data that is being produced is enormous. And this just kind of showcases really how big this data actually is. As our computing power steadily increases, the data explosion will continue to drive innovations within all aspects of our lives. The Human Genome Project has launched a new era surrounding our understanding of biology and medical diseases. This includes identifying the underlying genetic markers for some of nature's cruelest genetic mutations. As we shift our focus towards leveraging this knowledge towards saving lives, there will be an explosion of data that will need to be managed. And we can see on the left-hand side an article from NBC News set up on July 7th, 2015, talking about the amount of data surrounding the Human Genome Project. So when you start comparing one human's genetic composition against another, there's a wide variety of information there. And then when you compare that against other species, we see that the amount of data is just enormous. This voluminous data will require a more robust infrastructure in order to capitalize on the benefits that genomic data has to offer. The article suggests that the broader scientific community is ill prepared to handle data reaching into the exabyte threshold. This example showcases that as we are getting smarter and generating significant volumes of data, we need to ensure that our infrastructures are keeping up. This volume of information can be separated into two distinct data types: structured and unstructured data. Structured data is data organized in a highly mechanized or manageable manner. Some examples include data tables, OLAP cubes, XML format, etc. Unstructured data, on the other hand, it relates to raw and unorganized data, which can be cumbersome and costly to work with. Some examples include news articles, social media, video, images, email, etc. Merrill Lynch projected that 80 to 90% of all potential usable information exists in unstructured form. In 2010, Computer World claimed that unstructured information might account for 70 to 80% of all data in an organization. The Cisco IP traffic forecast projects that video will account for 61% of the total internet data in 2015. Software AG, Oracle Corporation, IBM, Microsoft, SAP, EMC, HP, and Dell have spent more than $15 billion on software firms only specializing in data management and analytics. In 2010, this industry on its own was worth more than $100 billion and was growing at almost 10% a year, about twice as fast as the software business as a whole. Well, what exactly is big data? Big data is a collection of data sets that are so large that they become difficult to process with traditional database management tools. This requires a new set of tools and techniques to manage the data. The big data concept is somewhat ambiguous and is used interchangeably with unstructured data analysis, social media, web analytics, and growing data needs that exceeds the organizational capabilities. A simple guideline for determining whether or not an organization is in the big data realm can be based on the size of the data sets that they're working with. Generally, data sets that are many terabytes to petabytes in size would fall into the big data family. Here's a graphic that shows as a business is becoming more sophisticated, moving beyond just their ERP system up to CRM and weblog information, that the volume of data and the complexity of data increases, and that moves us into the big data space. And my explanation and definition of big data was fairly narrow in the previous slide, and that was intended just to kind of keep our focus on what really matters with big data. So I'm sure if you talk to some colleagues who operate in this space, they might have differing viewpoints on it. But I think as the lecture goes on and we start diving into these technologies, it will become a little more clear. Well, when is our problem big enough for big data? We should use big data technologies when conventional processing tools won't work on our data. Additionally, when our data is really big, as described previously. We should use big data technologies when we can't fit or process the data in our favorite database or file system. So our SQL Server can no longer keep up, or our MySQL. If our data is really diverse, this is where some of the benefits of big data really come into play. And this includes working with semi-structured, like JSON, XML, logs, images, and sounds. And finally, we should use big data technologies when we have the IT infrastructure that can handle managing it. So this, if you're a whiz at programming piece, really is implying that the sophistication from an IT perspective of working with these technologies is quite advanced, and you need to make sure you have the support staff that can handle it. Well, when should we not use big data technologies? Well, when our definition doesn't fit in the previous section, and if we're in a hurry. So if we want to get the job done quickly and make an analysis perhaps on an ad hoc fashion, well, big data is not the approach to use. So why should I care about big data? It's a great question. Many people consider big data solutions to be a new way to do data warehousing when the volume of data exceeds the capacity or cost limitations for relational database systems. However, it can be difficult to fully grasp what big data solutions really involve, what hardware and software they use, and how and when they are useful. It is important that we are able to break through any misconceptions regarding big data and drive towards realizable value. And we can see this on the graphic on the left-hand side when we talk about business users and what they understand regarding big data. We can see that some of the problems are turning it into useful information. The actual working with the data. There are some security and privacy issues, and then there are some legal issues. So really the challenge is to take this large variety of information or data and turn it into information. Okay, and when we do that, that's where we extract the value. There are some basic questions, the answers to which will help you understand where big data solutions are useful and how you might approach the topic in terms of implementing your own solutions. Why do I need a big data solution? What problems do big data solutions solve? How is a big data solution different from traditional database systems? Will a big data solution replace my relational databases? I want to show a little bit of a Google trend analysis, just kind of talking about the broader state of analytics as a whole. So if we see business intelligence queries to Google, we find that they're kind of downward sloping, they've kind of flattened out a little bit. And we see in the US that pretty much the main urban populations are represented here. We also see an increase during the same period in the rise of business analytics. So more people are less interested in business intelligence as they are in business analytics, just in a general trending sense. Furthermore, we can see the topic of big data is becoming more prolific. And finally, we're going to talk about Hadoop, which is the underlying technology driving big data. And when we look at where most of the interest related to Hadoop is related, we see that it's actually in California, in the Silicon Valley. Well, why do I need a big data solution? Organizations will need a big data solution to enable them to survive in an increasingly competitive market where the sources and the requirements to store data are growing at exponential rate. Big data solutions are typically used for storing huge volumes of unstructured or semi-structured data, finding hidden insights in large stores of data from multiple devices, the so-called Internet of Things. So we're going to have sensors in our house that are going to be collecting information related to our living habits. It could be our thermostat on the wall. It could be our smartwatch. It could be a scale in your refrigerator. But all this information has to go somewhere and it has to be leveraged in the so-called Internet of Things. We need to use big data solutions when we're trying to extract vital management information. Big data solutions provide a way to help you discover value, which often cannot be measured just through traditional business methods such as cost and revenue analysis. So because of the types of data being different, there are now new analytics that can be introduced. And big data solutions are the vehicle that will help get us Big data is often described as a solution to the 3 V's problem. But what are the 3 V's? The first V is volume. Big data solutions are designed and built to store and process hundreds of petabytes of data in a way that can dramatically reduce storage cost. Processing systems must be scalable to handle increasing volumes. And that's an important aspect of big data solutions, is the scalability of the solution. Variety. Organizations often collect unstructured data, which is not in a format that suits relational database systems. This means that applying schemas to the data before or during storage is no longer a practical proposition. So because of all the different variety of sources, utilizing conventional data warehousing techniques is no longer sufficient. And when you have a large variety of the source of information, that's really where big data solutions thrive. And finally, we have velocity. And data is being collected at an increasing rate from many new types of devices and from a fast-growing number of users. The design and implementation of storage must be able to manage this efficiently, and processing systems must be able to return results within an acceptable time frame. This velocity aspect is one that we're really kind of seeing come into its own. When I go to Google and I'm searching through the search bar, it is remembering my search history, and it is providing me results in real time, and it is adapting to my individual search preferences and user profile. And now when I go on my iPhone and I'm logged into my Google account there, utilizing their service, that information is being transmitted very quickly to my desktop. So all of the aspects related to my user ID are moving into a centralized fashion, and the speed in which this information is being processed really presents some architectural challenges that have to be solved through big data solutions. The combination of all these factors means that in some circumstances, a big data batch processing solution may be a more practical proposition than a traditional relational database system. It's not always the case. You really have to look very carefully at the systems and what you're trying to achieve, but there are times that big data is more practical. However, as big data solutions have continued to evolve, it has become clear that they can also be used in a fundamentally different context. They can be leveraged to quickly get insights into data and to provide a platform for further investigation in a way that just isn't possible with traditional data storage, management, and querying tools. Big data solutions aren't all about business topics such as customer sentiment or web server log file analysis. They have many diverse uses around the world and across all types of applications. For example, police forces are using big data techniques to predict crime patterns. Researchers are using them to explore the human genome, as discussed earlier. Particle physicists are using them to search for information about the structure of matter. Astronomers are using them to plot the entire universe. And that's what we in the business would call big data. Mapping the universe is no small feat. Traditional database systems typically use a relational model where all the data is stored using predetermined schemas and linked using the values in specific columns of each table. Requiring a schema to be applied when data is written may mean that some information hidden in the data is lost. There are some more flexible mechanisms, such as the ability to store XML documents and binary data, but the capabilities for handling these types of data are usually quite limited. So we have our data sitting in some type of structured manner. We design our schema to map the data, and then it is processed in our relational system, and then we receive our output. Okay, that is our traditional database system in a very simple sense. Big data solutions do not force a schema onto the stored data. Instead, you can store almost any type of structured, semi-structured, or unstructured data and then apply a suitable schema when you query this data. Big data solutions store the data in its raw format and apply a schema only when the data is read, which preserves all of the information within the data. So this idea of applying the schema when you're reading the data, as close to the data as possible, is really the driving mechanism of what makes big data solutions so interesting and so powerful. Traditional database systems typically consist of a central node where all processing takes place, which means that all the data from storage must be moved to the central location for processing. The capacity of the central node can be increased only by scaling up, and there is a physical limitation on the number of CPUs and memory, depending on the chosen hardware platform. The consequence of this is a limitation of processing capacity, as well as a network latency when the data is moved to the central node. In contrast, big data solutions are optimized for storing vast quantities of data using simple file formats and highly distributed storage mechanisms, and the initial processing of the data occurs at each storage node. This means that, assuming you have already loaded the data into the cluster storage, the bulk of the data does not need to be moved over the network for processing. And we'll get into the advantages that we see from this a little later. This figure shows some of the basic differences between a relational database system and a big data solution in terms of storing and querying data. Now notice how both relational databases and big data solutions use a cluster of servers. The main difference is where the querying processing takes place and how the data is moved across the network. So the data is being processed closer to the data in a big data solution. And we'll describe this mechanism in detail, so don't worry. We're just kind of really getting the overview right now. Modern data warehouse systems typically use high-speed fiber networks, in-memory caching, and indexes to minimize data transfer delays. However, in a big data solution, only the results of the distributed query processing are passed across the cluster network to the node that will assemble them into a final results set. Under ideal conditions, performance during the initial stages of the query is limited only by the speed and capacity of connectivity to the co-located disk subsystem. And this initial processing occurs in parallel across all of the cluster nodes. So this parallel processing is really a big deal and allows you to draw from the strength of your hardware and computing resources. The ability to work with highly distributed data and simple file formats also opens up opportunities for more efficient and more comprehensive data collection. For example, services and applications can store data in any of the predefined distributed locations without needing to pre-process it or execute queries that can absorb processing capacity. Data is simply appended to the files in the data store. So as this data is being produced, we're just grabbing the data and we're storing it in a very elegant manner. So then when we want to go back and look at the data, we have all of our pieces in place. And it does this very efficiently. Any processing required on the data is done when it is queried, without affecting the original data and risking losing valuable information. And that's important. So the processing only occurs when it's queried. Queries to extract information in a big data solution are typically batch operations that may take some time to return a final result. However, when you consider the volumes of data that big data solutions can handle, the fact that queries run as multiple tasks on distributed servers does offer a level of performance that may not be achievable by other methods. While it is possible to perform real-time queries, typically you will run the query and store the results for use within your existing BI tools and analytics systems. And this is an important point. So as we're collecting this information and we're storing it in these big data environments, to actually do the processing on the data, it sometimes takes a while. These are very large volumes of information. And what we do is then when we take the results of our query, then we store this information from our BI platform into a conventional data warehouse, and then we use it, and then we draw from it utilizing our normal traditional techniques. This means that big data queries are typically not executed repeatedly as part of an application's execution, and so batch operation is not a major disadvantage. Big data systems are also designed to be highly resilient against failure of storage, networks, and processing. The distributed processing and replicated storage model is fault tolerant and allows easy re-execution of individual stages of the process. The capability for easy scaling of resources also helps to resolve operational and performance issues. So big data systems are designed to be highly resilient. So if a component of it fails, the entire system still remains intact. The following table summarizes the major differences between a big data solution and existing relational database systems. So if you want to understand the difference between schemas or read and write patterns, scalability, this is a useful resource to come back to. Big data batch processing solutions offer a way to avoid storage limitations or to reduce the cost of storage and processing for huge and growing volumes of data. This is especially true where this data might not be part of a vital business function. But this isn't to say that relational databases are no longer essential. Big data solutions will not replace your relational database. Continual development of the hardware and software for this core business function provides capabilities for storing very large amounts of data. In fact, the relational database systems we use today and the more recent big data batch processing solutions are complementary mechanisms. So you can almost kind of think of them as a symbiotic relationship or complementary. Big data batch processing solutions are extremely unlikely ever to replace the existing relational database. In the majority of cases, they complement and augment the capabilities for managing data and generating BI. And so when you're thinking about big data from a data scientist perspective, and going back to some of our previous lectures about using the R language and some of the machine learning techniques, think of big data as a way to collect the information and then process the information in such a way that we can derive more insights. The systems themselves, while they function differently on a technical level, they really are complementary in the sense. So as we're approaching these solutions, just make sure that if you're going to have a big data solution that you're going to put in place, you better also make sure you have a good relational database system in place as well. Otherwise, you're not going to be able to draw from it as effectively as you'd like. For an example, it's common to use a big data query to create a result set that is then stored in a relational database for use in the generation of BI or as an input to another process. And when we get into our practical example later in this lecture, we will see that we're going to be drawing from our big data solution to create data frames, and then from the data frame, then we can deploy our normal techniques. It's just a question of what you do with the data frame. Big data is also a valuable tool when you need to handle data that is arriving very quickly and which you can process later. So the velocity aspect of the 3 V's. We can dump the data into the storage cluster in its original format and then process it when required using a query that extracts the required result set and stores it in a relational database or makes it available for reporting. This complementary based system allows for us to deploy our full arsenal of machine learning techniques and an infrastructure highly suitable for data science. So now let's get into some of the ideas related to how big data solutions work. In the days before structured query language and relational databases, data was typically stored in flat files, often of which is a simple text format with fixed width columns. So here's an example on the right-hand side of a typical spreadsheet with column headers of a fixed width and data that sits underneath. Application code would open and read one or more of the files sequentially, or jump to specific locations based on the known line width of a row to read the text and parse it into columns to extract the values. Results would be written back by creating a new copy of the file or a separate results file. Modern relational databases put an end to all of this, giving us greater power and additional capabilities for extracting information simply by writing queries in a standard format such as SQL. The database system hides all the complexity of the underlying storage mechanism and the logic for assembling the query that extracts and formats the information. However, as the volume of data that we collect continues to increase and the native structure of this information is less clearly defined, we are moving beyond the capabilities of even enterprise-level relational database systems. At the core of many big data implementations is an open source technology named Apache Hadoop. Hadoop was developed by Yahoo, and the code was then provided as open source to the Apache Software Foundation. So the Apache Software Foundation produces a lot of different open source projects. And so when we're talking about big data and the technologies that drive it, there are a number of tools that you can use. All of these different icons represent different aspects of a big data environment. And we're going to get into all of these aspects in some detail upcoming, but just understand that Apache is really the driver of big data. Okay, and it's the foundation in which all of these technologies exist. Well, why Hadoop? Here's an interesting post that is just looking at job postings and the percentage of matching job postings when you're searching for HTML5 jobs, Hadoop jobs, or SAS jobs. And what I find really interesting on this is that you see a couple years ago, a lot of industries were really looking for SAS programmers. But with the advent of R and Python really kind of gaining mainstream notoriety, we see that SAS is becoming less prevalent. But we see Hadoop is consistently making grounds, and same with HTML5. So if you want to get in where the action is in terms of data science, you should be looking at these big data technologies, and in particular, you should have a skill set related to Hadoop. Well, we've mentioned Hadoop. Well, what is Hadoop exactly? Hadoop was created by Doug Cutting and Mike Kafarala in 2005. The name Hadoop was given by one of Doug Cutting's sons to that son's toy elephant. Doug used the name for his open source project because it was easy to pronounce and to Google. As of 2013, Hadoop adoption is widespread. For example, more than half of the Fortune 50 use Hadoop. The Apache Hadoop software library is a framework written in Java that allows for the distributed processing of large data sets across clusters of computers using simple programming models. It is designed to scale up from single computers to thousands of machines, each offering local computation and storage. Rather than rely on hardware to deliver high availability, the library itself is designed to detect and handle failures at the application layer, so delivering a highly available service on top of a cluster of computers, each of which may be prone to failures. So as we talked about a little earlier, we can take additional computers and we can scale up. So once you have a Hadoop ecosystem put into place, to add another computer is very straightforward and it's fairly simple. And more importantly, if one of the computers in your Hadoop cluster fail, to replace it and to bring in a new piece of hardware is also very straightforward. It's actually designed to accommodate that. All the modules in Hadoop are designed with a fundamental assumption that hardware failures of individual machines or racks of machines are commonplace and thus should be automatically handled in software by the framework. If there is a hardware that needs replacement, we can swap out the defective piece and replace it with a higher performing machine. And I'm using the analogy here on my image of a line change in the sport hockey. So you're taking your tired players and you're putting them to the bench, and then you're bringing a new unit of players that are fresh bodies that can perform the work. The Hadoop architecture allows for new hardware to be installed and scaled up without having to rewrite the underlying code. And a key point, once you have your Hadoop system operational, you can expand and build up the performance seamlessly. The hard work is done. You've done the hard work up front. Hadoop can also be deployed in traditional on-site data centers, but has also been implemented in public cloud spaces such as Microsoft Azure, Amazon Web Services, Google Compute Engine, IBM Bluemix, and many, many others. Here are some examples of cloud-based platforms. Azure HD Insight is a service that deploys Hadoop on Microsoft Azure. HD Insight uses a Windows-based Hadoop distribution that was jointly developed with Hortonworks and allows programming extensions with .NET. So if you're a Microsoft user, there's a big data solution in the cloud available for you, and it's leveraging the Hortonworks platform. It is possible to run Hadoop on Amazon Elastic Compute Cloud, EC2, and Amazon Simple Storage Service, S3. So if you like to have your cloud storage running through Amazon, you could run Hadoop on top of that. An interesting example of which is that the New York Times used 100 Amazon EC2 instances and a Hadoop application to process 4 terabytes of raw image TIFF data into 11 million finished PDFs in the space of 24 hours at a computation cost of about $240. Whenever I think of cloud technologies and all the buzz around cloud, I just go back to this fun little image and it just makes me smile. So I hope you enjoy this one. Well, what is Hadoop? So let's talk a little more about Apache Hadoop and what's the inner workings and mechanics of it. So the core consists of the Hadoop common package, or the kernel in this sense, a storage component, which is called HDFS, which also means the Hadoop Distributed File System. And we will get into this in great detail. A data processing component, the MapReduce framework, either MapReduce or MapReduce 1, or Yarn or MapReduce 2, depending on how you want to go about it. We will talk about Hadoop 2.0 in the upcoming slides as well. So we're first going to introduce the concept of MapReduce in the framework, how it works, and then we're going to talk about modern approaches in the MapReduce 2.0. Then we also have a runtime resource manager that allocates tasks and execute queries, such as these MapReduce jobs we're talking about and other applications. On top of this, we have other resources, tools, and utilities that run under the control of the resource manager, Yarn in this case, to support tasks such as managing data and running queries or other jobs on the data. So if some of this is confusing right now, don't worry about it. We will go through and we'll talk about it in detail, and hopefully it will be very clear. Now, one note, this approach allows the data to be processed faster and more efficiently than it would be in a more conventional supercomputer architecture that relies on a parallel file system where computation and data are connected via high-speed networking. The Hadoop Common Package contains the necessary Java archive, files, and scripts needed to start Hadoop. Hadoop requires Java Runtime Environment 1.6 or higher. The standard startup and shutdown scripts require that secure shell SSH be set up between nodes in the cluster. The package also provides source code documentation and a contribution section that includes projects from the Hadoop community. So when you're setting up your Hadoop environment, make sure you're working with your IT personnel on this, and the Java runtime environments, and making sure that the shells are working correctly. To me, is the function of IT and not necessarily a data scientist. The Hadoop Distributed File System, or HDFS, is a distributed file system designed to run on commodity hardware, as we had talked about. It has many similarities with existing distributed file systems. However, the differences from other distributed file systems are significant. HDFS is highly fault tolerant and is designed to be deployed on low-cost hardware. HDFS provides high throughput access to application data and is suitable for applications that have large data sets. So this really is kind of the file system that drives big data. HDFS supports a traditional hierarchical file organization. So when I think of my computer and how my files are located, I go to my computer if you're a Windows user, and then you open up your C drive and you see all these folders, and underneath the folders might be subfolders, and then the files are stored there. This is also very similar when working in HDFS. A user or an application can create directories and store files inside these directories. The file system namespace hierarchy is similar to most other existing file systems. One can create and remove files, move a file from one directory to another, or rename a file. HDFS does not yet implement user quotas. So when you think of well, what is HDFS, related to, my computer or my C drive? You can think of them kind of as similar aspects. Okay, so, how you interact and work with them is fairly similar and transferable. HDFS does not support hard links or soft links. However, the HDFS architecture does not preclude implementing these features. So even though it doesn't support it right now, maybe down the road we might actually see some of these hard or soft links being incorporated. There are some assumptions and goals that underlie HDFS. One is that it is a simple coherency model. HDFS applications need a write once, read many access model for files. A file once created, written, and closed need not be changed. This assumption simplifies data coherency issues and enables high throughput data access. Moving computation is cheaper than moving data. And this is something that whenever you're thinking about HDFS and big data, and you're trying to explain this to non-technical users, just remember this saying, because I think it's very useful. A computation requested by an application is much more efficient if it is executed near the data it operates on. This is especially true when the size of the data is huge. So if you have large volumes of information, you want to move the computation closer to the data. This minimizes network congestion and increases the overall throughput of the system. The assumption is that it is often better to migrate the computation closer to where the data is located rather than moving the data to where the application is running. HDFS provides interfaces for applications to move themselves closer to where the data is located. Portability across heterogeneous hardware and software platforms. HDFS has been designed to be easily portable from one platform to another. This facilitates widespread adoption of HDFS as a platform of choice for a large set of applications. And when we get into some more of the intricacies of handling big data and some of the other applications, we find that HDFS, the way it was set up originally, allows for these pieces to be put on top. It was designed that way, and that's one of its strengths. HDFS is designed to reliably store very large files across machines in a large cluster. It stores each file as a sequence of blocks. All blocks in a file except the last block are the same size. The blocks of a file are replicated for fault tolerance. Typically, 3 replicas are created. The block size and replication factor are configurable per file. An application can specify the number of replicas of a file. So when we're talking about this fault tolerance and, hey, when one computer goes down, even though I'm storing information on this computer, how do I just replace one and put a new one in and it knows where the data is? Well, these replicas that are created, typically 3, kind of handle the back-end aspects of that. Okay, and the HDFS system and platform, it handles the movement of this type of data. But just understand that, you might have 3 replicas of the information, being created, and you can configure that. The replication factor can be specified at file creation time, and it can be changed later. Files in HDFS are write once and have strictly one writer at any time. And this is a fundamental concept of working with big data. In order to set up the HDFS environment, we need to identify which computers or servers act as the primary repository of the data. In this case, we call it the name node. Okay, and so now we're going to start introducing some of the terminology. So, when you're going back and revisiting this lecture, just, when you're looking at data nodes and name nodes, and, we start getting into the zookeeper concept, just, it can be quite confusing, but just come back and you'll be okay. Additionally, we need to identify those which contain pieces of data. We call these the data nodes in the cluster. The name node and data node are pieces of software designed to run on commodity machines. A typical deployment has a dedicated machine that runs only the name node software. So we have one central computer or server that runs name node, and then on all of the other computers in our cluster or servers in our cluster, we run the data node software. Each of the other machines in the cluster runs one instance of the data node software, so only one. And one important note, these machines typically run on a Linux operating system. So when setting up your big data environment, I think it's advantageous to use Linux as your platform. And because this is a data science series of lectures, and we've talked a lot about the R programming language, one interesting aspect is that I use RStudio as my IDE of choice, and there's some great Linux support of RStudio. So when you're thinking about building your stack and your ecosystem of data science and machine learning, consider using the Linux platform for this reason, because you can integrate the technologies. The architecture does not preclude running multiple data nodes on the same machine, but in a real deployment, that this is rarely the case. The existence of a single name node in a cluster greatly simplifies the architecture of the system. The system is designed in such a way that the data never flows through the name node. So when thinking about building your big data environment, just remember, you could have multiple data nodes on the same machine. You could have multiple name nodes on the same machine. But if you create a more simplistic environment, as you're scaling up and as you're working with the data and drawing your insights, you can change the architecture as your computing needs require it. And of course, you would work with your CIO, to design, the correct system. But generally speaking, you want the simplest architecture that you can come up with, because as you're going to see, working with the data can be quite complex. The name node maintains the file system namespace and determines the mapping of blocks to data nodes. Any change to the file system namespace or its properties is recorded by the name node. The name node makes all decisions regarding replication of blocks. An application can specify the number of replicas of a file that should be maintained by HDFS. This information is stored by the name node. The name node executes file system namespace operations like opening, closing, and renaming files and directories. The name node periodically receives a heartbeat and a block report from each of the data nodes in the cluster. Receipt of a heartbeat implies that the data node is functioning properly. So it's kind of a diagnostic that goes on behind the scenes just to say, hey, is the data node working correctly? If it's not, what should we do to ensure that the entire system is working correctly? A block report contains a list of all blocks on a data node. Internally, a file is split into one or more blocks, and these blocks are stored in a set of data nodes. The data nodes are responsible for serving read and write requests from the file system's clients. The data nodes also perform block creation, deletion, and replication upon instruction from the name node. For effective scheduling of work, every Hadoop-compatible file system should provide a location awareness, the name of the rack, more precisely of the network switch, where a worker node is. Hadoop applications can use this information to run work on the node where the data is, and, failing that, on the same rack switch, reducing backbone traffic. HDFS uses this method when replicating data to try to keep different copies of the data on different racks. The goal is to reduce the impact of a rack power outage or switch failure so that even if these events occur, the data may still be readable. So the HDFS system really is handling a lot of aspects behind the scene to ensure the integrity of the system. A small Hadoop cluster includes a single master and multiple worker nodes. The master node consists of a job tracker, task tracker, name node, and data node. A slave or worker node acts as both a data node and task tracker, though it is possible to have data-only worker nodes and compute-only worker nodes. These are normally used only in non-standard applications. So when we're thinking about big data systems, just understand that you're going to have individual worker nodes. In a larger cluster, the HDFS is managed through a dedicated name node server to host the file system index. There is also a secondary name node that can generate snapshots of the name node's memory structures, thus preventing file system corruption and reducing loss of data. Similarly, a standalone job tracker server can manage job scheduling. In clusters where the Hadoop MapReduce engine is deployed against an alternate file system, the name node, secondary name node, and data node architecture of HDFS are replaced by the file system specific equivalents. So in highly complex big data systems, we find that we can have multiple versions of these name nodes, and we can have a primary and a secondary, okay, and it's entirely dependent on the way you want to handle your data and when there are faults in the system. The data store running each server in a cluster is a suitable distributed storage service such as HDFS or a compatible equivalent. Hadoop implementations may use a cluster where all the servers are co-located in the same data center. This is in order to minimize bandwidth use and maximize query performance. The data store in a Hadoop implementation is usually referred to as a NoSQL store. Although this is not technically accurate because some implementations do support a structured query language such as SQL. In fact, some people prefer to use the term not only SQL for just this reason. The particular suitability of a given NoSQL database depends on the problem it must solve. There are more than 100 plus NoSQL data store implementations available at this time of writing. So we have SQL and NoSQL. And so if I have my data in a highly mechanized manner with a lot of structure, I can use existing data warehouses and query it through SQL. But if I have widely varied types of information, then we start moving into these NoSQL platforms. And as you can see, with over 100 plus different variants of this, finding the right solution can be tricky. And you have to really look at the type of question you're trying to solve. These NoSQL data stores can be divided into the following basic categories. Key value stores. These are data stores that hold data as a series of key value pairs. There is no fixed schema for the data, and so these types of data store are ideal for unstructured data. Document stores. These are data stores optimized to hold structured, semi-structured, and unstructured data items such as JSON objects, XML documents, and binary data. They are usually indexed stores. Column data stores. These are data stores that use a schema, but the schema can contain families of columns rather than just single columns. They are ideally suited to storing semi-structured data where some columns can be predefined, but others are capable of storing differing elements of unstructured data. Graph data stores. These are data stores that hold the relationships between objects. They are less common than the other types of data store, many still being experimental, and they tend to have specialist uses. NoSQL storage is typically much cheaper than relational storage and usually supports a write once capability that allows only for the data to be appended. To update data in these stores, you must drop and recreate the relevant file, or maintain Delta files and implement mechanisms to conflate the data. This limitation maximizes throughput. Storage implementations are usually measured by throughput rather than capacity because this is usually the most significant factor for both storage and query efficiency. Now that we've talked about HDFS and data stores, we're going to move into the mechanism that really drives Hadoop. And this mechanism is called MapReduce, and we'll get into some of the fundamentals of how this works. Big data batch processing queries are commonly based on a distributed processing mechanism called MapReduce, often written as MapReduce, that provides optimum performance across the servers in a cluster. Map and reduce are mathematical operations. A map operation applies a function to a list of data items, returning a list of transformed items. A reduce operation applies a combining function that takes multiple lists and recursively generates an output. Okay, so some of these concepts are going to seem very abstract. We'll get through some of the mechanisms and we'll kind of show it visually. And I hope when we go through our practical example at the end of the tutorial, that it's very clear how map and reduce works. Because I think really to understand it, you have to see it firsthand. In a big data framework such as Hadoop, a MapReduce query uses two components, usually written in Java, which implement the algorithms that perform a two-stage data extraction and rollup process. So we talked a little bit about this just a moment ago. The map component runs on each data node server in the cluster, extracting data that matches the query and optionally applying some processing or transformation to the data to acquire the required result set from the files on that server. The reduce component runs on one or more of the data node servers and combines the results from all of the map components into the final result set. And I think one way to visually think about this is if you think of a submarine sandwich. You have on all these data node servers different pieces. You might have your bread, one, you might have your lunch meat, the cucumber, the green pepper, the onion, so on and so forth. So you map all the pieces that are required for your final submarine sandwich, and it takes just the elements of what it needs in order to produce the sum, reduces it down, and then it creates the final product. Okay, so you can think of, you have to map the data, and then you have to reduce it into just the components that you're working with in order to produce your final result. Let's look at a simplified example of a MapReduce query. We will assume that the input data contains a list of the detail lines from customer orders. Each detail line contains a reference, a foreign key that links it to the main order record, the name of the item ordered, and the quantity ordered. If this data was stored in a relational database using SQL, a query of the following form could be used to generate a summary of the total number of items sold. So I'm going to assume here that we at least have a functional understanding of SQL. So when you look at the syntax here and you look at this particular query, we're selecting the name of a product, the total quantity of the product from some table grouped by the name of the product. Okay, and if you need to freshen up on some SQL, there's some fantastic tutorials out there, but we're really not going to focus on that here. The equivalent using a big data solution requires a map and reduce component. The map component running on each node operates on a subset or chunk of the data. It transforms each order line into a name-value pair where the name is the product name and the value is the quantity from that order line. So these name-value pairs are very important in the MapReduce framework. And when we get into our example at the end, you will understand a little more how this works. Note that in this example, the map component does not sum the quantity for each product. It simply transforms the data into a list. Next, the framework shuffles and sorts all of the lists generated by the map component instances into a single list. Then the routine executes the reduce component with this list as the input. The reduce component sums the totals for each product and outputs the results. So if we look just using chunks of data represented with a color, and we look at both the map, the shuffle, and the reduce section, this chart becomes a very powerful visual image of what's going on behind the scenes. So we have our data sitting on our data node. It could be blue, could be red, could be yellow. The MapReduce framework is launched. Okay, the data is shuffled into the red, the yellow, and the blue components, and then it is reduced down and aggregated into just the red, yellow, and blue components, and then brought to our final result set. Depending on the configuration of the query job, there may be more than one reduce component instance running. The output from each map component instance is stored in a buffer on disk, and the component exits. The content of the buffer is then sorted and passed to one or more reduce component instances. Intermediate results are stored in the buffer until the final reduce component instance combines them all. So this is kind of getting into some of the underpinnings of really what MapReduce is doing. We're not going to really get much more technical than this, but just understand that it can be a very complex procedure, okay? And you can run more than one instance concurrently with each other, okay? But the end result is that in your reduce component, it combines all of the pieces in the shuffle and map instance of it and brings you to your output. In some cases, the process might include an additional component called a combiner that runs on each data node as part of the map process and performs a reduce type of operation on this part of the data each time the map process runs. It may also run as part of the reduce phase and again when the large data sets are being merged. In the example shown here, a combiner would sum the values for each word count so that the output is smaller, which can reduce network load and memory requirements, with a subsequent increase in overall query efficiency. So when I was first learning about big data techniques and the MapReduce concept, I just assumed you have your map and you have your reduce. But when you have very large volumes of data, okay, so really talking the biggest of the big data, sometimes the data is so massive that we want to be reducing it not only in the mapping stage, but also in the reducing stage. Because by the time you get to the output of your job, we could be talking about terabytes and petabytes and exabytes amount of data. So developing robust MapReduce mechanisms and utilizing this combiner component at the correct stages of our MapReduce query helps us get to the result data set that we want. So when you're thinking about MapReducing and the complexity of the work that you're doing, you need to understand that sometimes there are advantages of having simpler MapReduces frameworks, and there are other times where it is more beneficial to incorporate some of this combiners. Performing a MapReduce operation involves several stages, such as partitioning the input data, reading and writing data, and shuffling and sorting the intermediate results. Some of these operations are quite complex, as we had noted in the previous slides. However, they are typically the same every time, irrespective of the actual data and the query. And this is important because once you get the hang of MapReduce and how to write and work with the data, as soon as you have that eureka moment, you're going to be able to copy and use the same techniques for different type of analytical problems. So once you get through that learning curve, working with HDFS and MapReduce, the techniques are essentially the same each time. The framework does the rest. As all you have to do is create the map and reduce components, and Hadoop figures it all out. Okay, so behind the scenes, it's finding the most optimal way to move the query as close to the data as possible, and you just write the MapReduce components, and that's it. Although the core Hadoop engine requires the map and reduce components it executes to be written in Java, you can use other techniques to create them in the background without writing Java code. For example, you can use tools named Hive and Pig that are included in most big data frameworks to write queries in an SQL-like or a high-level scripting language. You can also use the Hadoop Streaming API to execute components written in other languages. We will go through an example later in the presentation of executing MapReduce jobs from the R language. So this is a really important aspect. So whether your preferred programming language is Python or R, you can invoke this MapReduce concept. You don't have to be a Java programmer. And when I look at my toolkit and what I'm most comfortable working with, I prefer to work in R. So fortunately for us, we have mechanisms that we can now draw from to do this type of work. And we will go through it, and I will walk through a MapReduce job from start to finish in R. Now let's talk about Yarn. The initial Hadoop framework has been refined into a new version, sometimes referred to as Hadoop 2.0. Apache Hadoop Yarn, which is in short for Yet Another Resource Negotiator, is a cluster management technology and one of the key features in second generation Hadoop. Originally described by Apache as a redesigned resource manager, Yarn is now characterized as a large-scale distributed operating system for big data applications. Think of this as the Windows environment of big data. Now, I couldn't find a nice little icon from Apache's website that represented Yarn, so I just put an image of some Yarn up in the top right-hand corner, and I found this beautiful picture of a happy little kitty playing in Yarn, and I thought, hey, I can't pass this one up. So I hope you like little kitties sleeping on Yarn. Yarn is a software rewrite that decouples MapReduce's resource management and scheduling capabilities from the data processing component, enabling Hadoop to support more varied processing approaches and a broader array of applications. So this is really important. This is the fundamental difference between the first generation Hadoop technology and Hadoop 2.0, or the Yarn framework. Before, a lot of the aspects were run directly in the MapReduce framework. Now it's being pulled out. For example, Hadoop clusters can now run interactive querying and streaming data applications simultaneously with MapReduce batch jobs. Okay, so this opens up a lot of the functionality that we're going to see related to the velocity component of our 3V problem. The original incarnation of Hadoop closely paired the Hadoop distributed file system with a batch-oriented MapReduce programming framework, which handles the resource management and job scheduling on Hadoop systems and supports the parsing and condensing of datasets in parallel. In 2012, Yarn became a sub-project of the larger Apache Hadoop project. Yarn combines a central resource manager that reconciles the way applications use Hadoop system resources with node manager agents that monitor the processing operations of individual cluster nodes. Separating HDFS from MapReduce with Yarn makes the Hadoop environment more suitable for operational applications that can't wait for batch jobs to finish. Hadoop has always been a catch-all for disparate open source initiatives that combine for a more or less unified big data architecture. Some would claim that Hadoop has always been, at its very heart, simply a distributed file system, HDFS. But the range of HDFS alternative databases, including HBase and Cassandra, undermines that assertion. Until recently, Hadoop has been down deep a specific job execution layer, MapReduce, that executes on one or more alternative massively parallel data persistence layers, one of which happens to be HDFS. So when you think of Hadoop, you have to think of MapReduce. But the recent introduction of the next generation execution layer for Hadoop, Yarn, eliminates the strict dependency of Hadoop environments on MapReduce. Just as critical, Yarn eliminates a job execution bottleneck that has bedeviled MapReduce from the start. The fact that all MapReduce jobs have had to run as batch processes through a single daemon, a single job tracker, a constraint that limits scalability and dampens processing speed. These MapReduce constraints have spurred many vendors to implement their own speedups, such as IBM's Adaptive MapReduce, to get around the bottleneck of native MapReduce. So when we go back to our big data landscape all the way at the beginning of the lecture and you see all these technologies, we see that the initial limitations in the MapReduce framework in the Hadoop environment had spawned some of these companies to come about and these products to come to market. All of this might make one wonder what specifically Hadoop means anymore in terms of an identifiable stack distinct from other big data and analytics platforms and tools. That's a definitional quibble. Yarn is a foundational component of the evolving big data mosaic. Yarn puts traditional Hadoop into a larger context of compostable, fit-to-purpose platforms for processing the full gamut of data management, analytics, and transactional computing jobs. Though it retains backward compatibility with the MapReduce API and continues to execute MapReduce jobs, a Yarn engine is capable of executing a wide range of jobs developed in other languages. So as we close this phase of the presentation, I think it's important that what we take out of this as data scientists is that if you're going to be building a big data environment, you should be thinking about Hadoop 2.0 and you should be leveraging Yarn. Now let's spend some time and kind of dive into this Hadoop 2.0 framework a little bit. There are a lot of moving pieces and exciting opportunities of what we can do with the data, and this part of the presentation is designed to expose us to exactly what these pieces are and how we can work with them. MapReduce is just one application that you can run on a Hadoop cluster. Several query management and other types of tools that can be used with Hadoop 2.0 are available or under development. Here are some examples from the Apache project. Okay, and we have HBase, Hive, Pig, Mahout, Kafka, Zookeeper, and Storm. And we'll dive into each one of these in detail in the upcoming slides. So if you want to learn about these technologies and what they're actually doing, so you can have an intelligent big data discussion, please feel free to pay close attention to the next portion of the presentation. It is important to note that this listing of tools and techniques are not all inclusive of all the technologies that can be utilized with Hadoop. For the sake of brevity, we will focus the next portion of this presentation going over the previously listed components in greater detail. This should provide a strong foundation for the potential and use of modern big data analytics platforms. However, I would recommend some further independent research to better understand the growing trends in the industry and when to deploy specific technologies that suits your big data application. Here's an overview of a typical Hadoop-based big data mechanism. So now we're getting into the Hadoop 2.0 and all of the different components that we have. So we have our resource manager, we have our Yarn that's managing the whole system. It's sitting on top of HDFS. We have our Hadoop Common in place so for our map reducing components. So that's the batch processing. But then we can use scripting language such as Pig, SQL-like queries such as Hive, NoSQL utilizing HBase. If we have streaming information, we'll use Storm. And then there are other aspects that we can use. And of course, in order to manage the system, we have to introduce some other type of technologies and techniques such as Oozie, Sqoop, and Zookeeper. And these are the main assets of the Apache Hadoop 2.0. And if you want to find more information about all of these specific components, please go to Apache Hadoop's website, and you can find a wonderful large amount of resources available there. It's quite technical, so you better be ready, for some technical discussions. But if you need to get to the heart of a particular issue, that's the first place I would look. The first component of the big data solution we will be providing an overview on within this lecture is related to an open source, non-relational distributed database modeled after Google's Bigtable. This is a NoSQL platform called HBase and is developed as part of the Apache Software Foundation's Hadoop project. The HBase platform is a column-oriented system which runs on top of HDFS. It provides real-time read-write access to those large data sets. With Yarn as the architectural center of Apache Hadoop, multiple data access engines such as Apache HBase interact with the data stored in the cluster. Tables in HBase can serve as the input and output for MapReduce jobs run in Hadoop and may be accessed through the Java API, but also through REST, Avro, or Thrift Gateway APIs. HBase features compression, in-memory operation, and Bloom filters on a per column basis as outlined in the original Bigtable paper. A Bloom filter, for those who are unaware, is a data structure designed to tell you rapidly and memory efficiently whether an element is present in a set. If the element is not in the Bloom filter, then we know for sure that we don't need to perform this expensive lookup. On the other hand, if it is in the Bloom filter, we perform the lookup and we can expect it to fail some proportion of the time, which is the false positive rate. Apache HBase provides a fault-tolerant way of storing large quantities of sparse data, small amounts of information caught within a large collection of empty or unimportant data. An example of this includes finding the 50 largest items in a group of 2 billion records, or finding the non-zero items representing less than 0.1% of a huge collection. HBase is not a direct replacement for a classic SQL database, although recently its performance has improved and it is now serving several data-driven websites, including Facebook's messaging platform. Apache HBase scales linearly to handle huge datasets with billions of rows and millions of columns, and it easily combines data sources that use a wide variety of different structures and schemas. Apache HBase provides random real-time access to your data in Hadoop. It was created for hosting very large tables, making it a great choice to store multi-structured or sparse data. Users can query HBase for a particular point in time, making flashback queries possible. These following examples make HBase a great choice for storing semi-structured data like log data and then providing that data very quickly to users or applications integrated with HBase. One company that provides web security services maintains a system accepting billions of event traces and activity logs from its customers' desktops every day. The company's programmers can tightly integrate their security solutions with HBase to assure that the protection that they provide keeps pace with real-time changes in the threat landscape. Another company provides stock market ticker plan data that its users query more than 30,000 times per second with an SLA of only a few milliseconds. Apache HBase provides that super low latency access over an enormous, rapidly changing data store. Enterprises use Apache HBase's low latency storage for scenarios that require real-time analysis and tabular data for end user applications. HBase scales linearly by requiring all tables to have a primary key. The key space is divided into sequential blocks that are then allocated to a region. Region servers own one or more regions, so the load is spread uniformly across the cluster. If the keys within a region are frequently accessed, HBase can further subdivide the region by splitting it automatically, so that manual data sharding is not necessary. Zookeeper and HMaster servers make information about the cluster topology available to clients, and we'll get more onto the Zookeeper concept a little later. Clients connect to these and download a list of region servers, the regions contained within those region servers, and the key ranges hosted by the regions. Clients know exactly where any piece of data is in HBase and can contact the region server directly without any need for a central coordinator. Region servers include a mem store to cache frequently accessed rows in memory. HBase provides high data availability in several ways. Highly available cluster topology information through production deployments with multiple HMaster and Zookeeper instances. Data distribution across many nodes means that loss of a single node only affects data stored on that node. HBase allows data storage, ensuring that the loss of a single node does not result in the loss of data availability. HFile File format stores data directly in HDFS. Each file can be read or written to by Apache Hive, Apache Pig, and MapReduce, permitting deep analytics on HBase without data movement. For further research on Apache HBase concepts and techniques, please refer back to the Apache Software Foundation's user forums. And you'll find for each of these techniques that we get into that if you want to learn more, please go back to Apache Software Foundation's forums. The second component of the big data solution we'll be providing an overview on within this lecture is related to conventional data warehouse techniques, but in a big data environment. The Apache Hive data warehouse software facilitates querying and managing large data sets residing in distributed storage. So Apache Hive is built on top of Apache Hadoop. It provides tools to enable easy data extract, transform, or load, or ETL, a mechanism to impose structure on a variety of data formats, access to files stored either directly in Apache HDFS or in other data storage systems such as Apache HBase, and query execution via MapReduce. So think of Hive as kind of your way of writing the SQL queries and actually manipulating the data. It's kind of the framework that uses an SQL-like query language. Okay, so I like to think of this as the data warehouse infrastructure for big data is Apache Hive. Hive defines a simple SQL-like query language called QL or HiveQL that enables users familiar with SQL to query the data. At the same time, this language also allows programmers who are familiar with the MapReduce framework to be able to plug in their custom mappers and reducers. This allows the user to perform more sophisticated analysis that may not be supported by the built-in capabilities of the language. QL can also be extended with custom scalar functions, aggregations, and table functions. So if you're familiar with SQL, working with HiveQL or QL, there is a learning curve to it, but I think you can draw from some of the same techniques when you're developing your queries. And in our practical example we'll get into in R, we'll see some examples of writing Hive queries. So we see a couple on the left-hand side here of just some of the syntax, but we'll get into it a little bit. Hive does not mandate read or written data be in the Hive format. There is no such thing. Hive works equally well on Thrift, controlled, limited, or specialized data formats. So Hive is kind of your one-stop shop of tools that's universal across all the different languages. So don't think of it as HiveQL as something special just for for big data environments. You can think of it as kind of a universal set of tools. Hive is not designed for OLTP workloads and does not offer real-time queries or row-level updates. It is best used for batch jobs over large sets of append-only data, like weblogs. What Hive values most are scalability, extensibility, fault tolerance, and loose coupling with its input formats. So that's one key thing that makes this different than a data warehouse environment. You're not going to be performing real-time queries or row-level updates with Hive. There are a couple of subcomponents of Hive which help aid in the data processing. These components are called hCatalog and WebHCat. hCatalog is a table and storage management layer for Hadoop that enables users with different processing tools, including Pig and MapReduce, to more easily read and write data on the grid. WebHCat provides a service that you can use to run Hadoop MapReduce or Yarn, Pig, Hive jobs, or perform Hive metadata operations using an HTTP interface. Like before, if you're interested in Hive, which I would definitely recommend checking out if you're really going to dive into big data topics, you need to have Hive under your belt. Go to the Apache Software Foundation's user forums. Now let's move to Apache Pig. Apache Pig is a platform for analyzing large data sets that consists of a high-level scripting language for expressing data analysis programs, coupled with infrastructure for evaluating those programs. The salient property of Pig programs is that their structure is amenable to substantial parallelization, which in turn enables them to handle very large data sets. At the present time, Pig's infrastructure layer consists of a compiler that produces sequences of MapReduce programs for which large-scale parallel implementations already exist. For example, the Hadoop subproject. Pig's language layer currently consists of a textual language called Pig Latin, which has the following key properties. It has an ease of programming. It is trivial to achieve parallel execution of simple, embarrassingly parallel data analysis tasks. Complex tasks comprised of multiple interrelated data transformations are explicitly encoded as data flow sequences, making them easy to write, understand, and maintain. Optimization opportunities. The way in which tasks are encoded permits the system to optimize their execution automatically, allowing the user to focus on semantics rather than efficiency. Extensibility. Users can create their own functions to do special purpose processing. Pig Latin is a simple query algebra that lets you express data transformations such as merging data sets, filtering them, and applying functions to records or group of records. Users can create their own functions to do special purpose processing. For example, here is a sample Pig script, if you will, and you can see the various components and how to invoke the script and what you actually get out as the output. Here's another example of a word count script in Pig. So this is just a simple script that's creating a word count in this case. And there's some annotation from here, so if you want to understand more about writing in Pig, please feel free to check out the wide variety of resources. Hortonworks actually has some really nice tutorials on Pig. So if you're looking for something good to get your feet wet in Pig, definitely check out Hortonworks. Now we're going to talk about Apache Mahout. The Apache Mahout project's goal is to build an environment for quickly creating scalable performance machine learning applications. The name Mahout was originally chosen for its association with the Apache Hadoop project. A Mahout is a person who drives an elephant, and in this case, because Hadoop's logo is an elephant, the machine learning who is driving the data on top, it's a very clever idea. They wanted a name that complements Hadoop, but the project managers see the project as a good driver of Hadoop in the sense that they'll be using and testing it. There are some notable machine learning techniques that is currently supported in the Mahout framework. So if I'm looking at machine learning and the data science, if you look at a lot of my previous lectures, talking about the various techniques and how to apply them, Mahout also has a framework in which you can apply some of these techniques. And here are some of the more notable ones that you can run through Mahout. The strength of Mahout is that it is designed to integrate seamlessly within the Yarn framework. However, the depth of machine learning and statistical algorithms is not on the same level as R or Python. So even though you have the Apache project and you have all its various components, Mahout being the machine learning piece of it, the sophistication and the capabilities of the machine learning within Mahout are fairly limited. For our purposes, it is important to know of the Apache Mahout project and its capabilities, even though this might not be the framework that we draw from for machine learning. And I think that's more than fair. You might find that there are some advantages of having everything running through the Yarn ecosystem, including the machine learning components. I personally prefer to do my machine learning in R. The project's community has decided to rework Mahout to support the increasingly popular Apache Spark in-memory data processing framework, as well as the H2O engine for running machine learning and mathematical workloads at scale. And if you remember H2O from our deep learning exercise, that's the example where we did some of the handwriting recognition. Okay, so H2O framework is a very powerful framework that we can use, for machine learning. And so the industry acronym is that taking the Spark in-memory computing plus H2O, that gives you sparkling water. While data processing in Hadoop has traditionally been done using MapReduce, the batch-oriented framework has fallen out of vogue as users began demanding lower latency processing for certain types of workloads, such as machine learning. So they want to be able to perform machine learning faster, and we find that just using the MapReduce framework, it isn't giving us the speed that we want. However, nobody really wants to abandon Hadoop entirely because it's still great for storing lots of data, and many still use MapReduce for most of their workloads. So if I have huge volumes of information and I need to work at it, MapReduce is a very powerful tool. But if I want to gain machine learning insights quickly and efficiently, it does have its limitations. I personally think MapReduce has a lot of value in big data contexts. Not everybody is going for the velocity aspect of the 3 V's problem. Sometimes just the volume is good enough. Now let's talk about Apache Oozie. Oozie is a workflow scheduler program to manage Apache Hadoop jobs. So I like to think of this as like SQL. For those who are familiar with the SQL Server, this is just your job manager. So if you have SSIS packages that you want to execute, or different jobs on a scheduler, Apache has their own version, and it's called Oozie. Oozie combines multiple jobs sequentially into one logical unit of work. It is integrated with the Hadoop stack, with Yarn as its architectural center, and supports Hadoop jobs for Apache MapReduce, Pig, Hive, and Scoop. Oozie is a scalable, reliable, and extensible system. Apache Oozie is a tool for Hadoop operations that allow cluster administrators to build more complex data transformations out of multiple component tasks. Oozie triggers workflow actions, but Hadoop MapReduce executes them. This allows Oozie to leverage other capabilities within the Hadoop stack to balance loads and handle failures. This provides greater control over jobs and also makes it easier to repeat those jobs at predetermined intervals. So if you're building your framework and you want to schedule your jobs to run, and you've written all these glorious HiveQL, Pig scripts, your MapReduce jobs, and you just want to get the data and the output and work on it for data science related purposes, you should be considering incorporating Oozie into the spectrum. At its core, Oozie helps administrators derive more value from Hadoop. Plain and simple. Oozie Bundle provides a way to package multiple coordinator and workflow jobs and to manage the lifecycle of those jobs. There are two basic types of Oozie jobs: Oozie workflow jobs, DAGs, specifying a sequence of actions to execute. The workflow job has to wait. Oozie coordinator jobs. These are recurrent Oozie workflow jobs that are triggered by time and data availability. An Oozie workflow is a collection of actions arranged in a directed acyclic graph, or a DAG. Control nodes define job chronology, setting rules for beginning and ending a workflow. In this way, Oozie controls the workflow execution path with decision fork, and join nodes. Action nodes trigger the execution of tasks. Oozie Coordinator can also manage multiple workflows that are dependent on the outcome of subsequent workflows. So when I think of what these workflows are, you can think of them kind of like an SSIS package in Microsoft SQL Server, for those who are familiar with it. The outputs of subsequent workflows become the input to the next workflow. This chain is called a data application pipeline. So you can move from one workflow to another, and you can connect these pipes, okay, creating a pipeline, if you will. Oozie detects completion of tasks through callback and polling. When Oozie starts a task, it provides a unique callback HTTP URL to the task, thereby notifying that URL when it's complete. If the task fails to invoke the callback URL, Oozie can pull the task for completion. Often, it is necessary to run Oozie workflows on regular time intervals, but in coordination with unpredictable levels of data availability or events. In these circumstances, Oozie Coordinator allows you to model workflow execution triggers in the form of the data time or event predicates. The workflow job is started after those predicates are satisfied. Now let's talk about Scoop. Apache Scoop efficiently transfers bulk data between Apache Hadoop and structured data stores such as relational databases. Scoop helps offload certain tasks such as ETL processing from the EDW to Hadoop for efficient execution at a much lower cost. Scoop can also be used to extract data from Hadoop and export it into external structured data stores. Scoop works with relational databases such as Teradata, Netezza, Oracle, MySQL, Postgres, and HSQLDB. So think of this as the mechanism to take data from your HDFS and move it into an SQL database. So Scoop is a very powerful tool in the Apache arsenal. Scoop provides a pluggable mechanism for optimal connectivity to external systems. The Scoop Extension API provides a convenient framework for building new connectors, which can be dropped into Scoop installations to provide connectivity to various systems. Scoop itself comes bundled with various connectors that can be used for popular database and data warehousing systems. This is a great mechanism to utilize when exploring how to bridge data analytics projects between conventional DW structures into the Hadoop HDFS approach and vice versa. Apache Zookeeper is a centralized service for maintaining configuration information, naming, providing distributed synchronization, and providing group services. So we talked a little bit about Zookeeper earlier, but you can think of this as kind of the keeper of all the settings of our various animals in the Apache framework. I think that's the way I envision it, at least. All of these kinds of services are used in some form or another by distributed applications. So when we look in the Hadoop 2.0 or the Yarn framework, we need to have effective mechanisms for managing this information, and that's essentially what this is. Each time they are implemented, there is a lot of work that goes into fixing bugs and race conditions that are inevitable. So whenever we add a new software or a new component to the structure, a lot of these naming conventions and how they interact with each other introduces a lot of bugs and problems. Because of the difficulty of implementing these kind of services, applications initially usually skimp on them, which make them brittle in the presence of change and difficult to manage. So rather than introducing different components to the various services because of all the connectivity issues across the ecosystem, generally the providers usually skimp on them, and that's not a good thing. We want the maximum features available to us, and we need a system to manage it, which is the Zookeeper. Even when done correctly, different implementations of these services lead to management complexity when the applications are deployed. Zookeeper's architecture supports high availability through redundant services. The clients can thus ask another Zookeeper leader if the first fails to answer. Zookeeper nodes store their data in a hierarchical namespace, much like a file system or a tree data structure. Zookeeper is used by companies including Rackspace, Yahoo, and eBay. Apache Kafka is an open source message broker project developed by the Apache Software Foundation. The project aims to provide a unified, high throughput, low latency platform for handling real-time data feeds. The design is heavily influenced by transaction logs. Kafka is often categorized as a messaging system, and it serves a similar role, but provides a fundamentally different abstraction. So Kafka is an important component of the velocity system. So as we move into Kafka and Storm, which is the next Apache platform we'll talk about, think of these as mechanisms that help move data quickly and give us information. The key abstraction in Kafka is a structured commit log of updates. Before we dive deeper into Kafka, let's take a look at the following example. We're going to try to simplify it as much as we can here. A message in its literal sense would be some information that needs to go from a source to a destination. When this information is sent from the source and is received by the destination, we state that the message has been delivered. For example, let us consider you and your friend using a long hollow pipe to talk to each other. When your friend speaks into it from one end, you would keep your ears to the other end to hear what he just said. In this way, you will receive the messages he would have to convey. In its simplest form, a message is nothing but data. A system that can handle transmission of data from a source to a destination is called a messaging system. In the computing world, the source could be a machine that is generating the data, for example, a web server generating a large number of logs, or a human user. In most cases, you will see the volumes generated by systems and machines to be way larger than ones generated by human beings. In a messaging system, you would want to ensure that the message is delivered to the target. Even if the target is not ready to receive it, there has to be a provision to hold it. To achieve this, the messaging system should provide a way of retaining the message in the medium of communication until the target is ready to receive it. However, in reality, the scenarios could be such that the messages may have to be delivered to more than one destination. With this understanding, let's give some technical labels to the different components in a messaging system. So the first is a publisher, and that is the source or the different sources that create messages. Then we have the subscriber. The destinations or targets are the one who read the message. In other words, they subscribe to the messages generated by the publishers. There is one more component that we still need to mention. So far, we have been referring to it as a channel medium to which publishers write data and from where subscribers read data. That is not entirely the correct way of referring to it. A more appropriate way would be to call it a log. Logs, in a general sense, stand for a record of what happened. In our context, the message can be classified as an event, and a log is what stores that event. Publishers publish events to the log, and the subscribers read these events from the log to know what happened. The following is a simple illustration of how a log appears. As you can see above, the log is a sequence of numbered messages that are appended only and ordered by time. The log in the database world is often referred to as the commit log. A producer of data sends a stream of records which are appended to this log, and any number of consumers can continually stream these updates off the tail of the log with millisecond latency. Each of these data consumers has its own position in the log and advances independently. This allows a reliable, ordered stream of updates to be distributed to each consumer. The log can be sharded and spread over a cluster of machines, and each shard is replicated for fault tolerance. This gives a model for parallel ordered consumption, which is key to Kafka's use as a change capture system for database updates, which must be delivered in order. Kafka is built as a modern distributed system. Data is replicated and partitioned over a cluster of machines that can grow and shrink transparently to the applications using the cluster. Consumers of data can be scaled out over a pool of machines as well and automatically adapt to failures in the consuming processes. The initial adoption is usually for a single, particularly large-scale use case. Log data feeds into Hadoop or other data streams beyond the capabilities of their existing messaging systems or infrastructure. From there, though, the usage spreads. Though the initial use case may have been feeding a Hadoop cluster, once there's a continual feed of events available, the use cases for processing these events in real time quickly emerge. Existing applications will end up tapping into the event streams to react to what is happening more intelligently, and new applications will be built to harness intelligence derived off these streams. So once these streams of information are fed beyond just regular processing in a Hadoop cluster, there's a lot more we can do with the speed of the information that's coming in. And that's really where Kafka shines. At a number of Silicon Valley companies today, you can see this concept in action. Everything from user activity to database changes to administrative actions like restarting a process are captured in real-time streams that are subscribed to and processed in real time. What is interesting about this is that what begins as simple plumbing quickly evolves into something much more. These data streams begin to act as a kind of central nervous system that applications organize themselves around. The final topic we're going to get into today, and thank you so much for diving into all these topics with me so far. I know it's a lot of information to be absorbing, but please feel free to go back and refer to the information. The final topic we're going to get into is Apache Storm. And what Apache Storm is it's a distributed, reliable, fault-tolerant system for real-time processing of data at high velocity. This is a key technology towards handling the velocity aspects of the 3 V's problem from earlier. Storm makes it easy to reliably process unbounded streams of data, doing for real-time processing what Hadoop did for batch processing and voluminous data. So Storm is a big deal in the big data, and if you're going to be doing any type of real-time work, you should be really paying close attention to what can be done in Storm. Storm was designed from the ground up to be usable with any programming language. Storm is fast. A benchmark clocked it at over 1 million tuples processed per second per node. It is scalable, fault-tolerant, and guarantees your data will be processed, and is fairly easy to set up and operate. Storm integrates with the querying and database technologies you already use. Apache Storm is a free and open source project. It has a large and growing ecosystem of libraries and tools to use in conjunction with Storm, and including everything from spouts, and these spouts integrate with querying systems such as JMS Kafka, Redis PubSub, and much more. Storm states, and Storm states make it easy to manage large amounts of in-memory state in your computations in a reliable fashion by using a distributed file system for persistence. And database integrations. These are helper bolts for integrating with various databases such as MongoDB, Cassandra, and much more. And so these spouts and storm states and these concepts, we'll dive into that a little bit here. But just understand that there are tools that help manage each one of these aspects. And there's of course other miscellaneous utilities. So what is Storm used for? Well, the Storm framework is primarily used for real-time analytics, online machine learning, continuous statistics computations, operational analytics, and it helps to enforce the extract, transform, and load paradigms, or the ETL paradigms. And if you want to understand some of the documentation for links to notable Storm-related projects hosted outside of Apache, you can find that from their website. Well, here's a list of some companies that are using Apache Storm. So a lot of these are big players in the industry right now. We have the Weather Channel, Twitter, Yelp, Groupon, WebMD, Alibaba, and so on and so forth. So Storm is a critical component in the big data environment. The core abstraction in Storm is the stream. A stream is an unbounded sequence of tuples. Storm provides the primitives for transforming a stream into a new stream in a distributed and reliable way. For example, we may want to transform a stream of tweets into a stream of trending topics. There are just 3 abstractions in Storm which work to process streams of data. The first is a spout. And a spout is a source of streams in a computation. Typically, a spout reads from a queuing broker such as Kafka, but a spout can also generate its own stream or read from somewhere like the Twitter streaming API, as we had just mentioned. We have bolts. Spouts passes streams of data to Bolt, which processes and passes it to either a data store or another Bolt. Bolts can do anything from run functions, it can filter tuples, it can do streaming aggregations, do streaming joins, talk to databases, and more. And the final aspect is a topology. A topology is a network of spouts and bolts, with each edge in the network representing a bolt subscribing to the output stream of some other spout or bolt. When programming on Storm, you manipulate and transform streams of tuples, and a tuple is a named list of values. So you can think of tuples in the Twitter sense as individual tweets. I think this is probably the easiest way to understand it. You can just think of it as a packet of information. Tuples can contain objects of any type. If you want to use an object type Storm doesn't know about, it's very easy to register a serializer for that type. So Storm isn't limited to just the types of data that it's aware of. You can register your own. To do real-time computation on Storm, you create what we call topologies. A Storm topology consumes streams of data and processes those streams in arbitrarily complex ways, repartitioning the streams between each stage of the computation however needed. A topology is an arbitrarily complex multi-stage stream computation. Topologies run indefinitely when deployed. When a spout or bolt emits a tuple to a stream, it sends the tuple to every bolt that subscribed to that stream. Each node in a Storm topology executes in parallel. In your topology, you can specify how much parallelism you want for each node, and then Storm will spawn that number of threads across the cluster to do the execution. And I think the key takeaway is that these topologies, they've run indefinitely when you deploy them. A Storm cluster is superficially similar to a Hadoop cluster. Whereas on Hadoop, you run MapReduce jobs. On Storm, you run topologies. Jobs and topologies themselves are very different. One key difference is that a MapReduce job eventually finishes, whereas a topology processes messages forever until we kill it. So it's kind of an infinitely recurring mechanism. There are two kinds of nodes on a Storm cluster, the master node and the worker nodes. The master node runs a daemon called Nimbus that is similar to Hadoop's job tracker. Nimbus is responsible for distributing code around the cluster, assigning tasks to machines, and monitoring for failures. Each worker node runs a daemon called the supervisor. The supervisor listens for work assigned to its machine and starts and stops worker processes as necessary based on what Nimbus has assigned to it. Each worker process executes a subset of topology. A running topology consists of many worker processes spread across many machines. All coordination between Nimbus and the supervisors is done through a Zookeeper cluster. Additionally, the Nimbus daemon and supervisor daemons are fail-fast and stateless. All state is kept in Zookeeper or on local disk. This means you can kill Nimbus or the supervisors and they'll start back up like nothing happened. So I kind of imagine this to be kind of like the Liquid Terminator in Terminator 2. I mean, you can shoot him and his bits will fly everywhere, but then they can come back together and keep the system afloat. So even though you can kill the Nimbus or the supervisors, they'll start back up and retain its original form. This design leads to Storm clusters being incredibly stable. Here we can see how the Apache Storm framework can be integrated with other aspects within your big data environment. So we can see how we have our HBase platform where we have our raw data in a NoSQL format. We can run MapReduce jobs and process the data, or we can, from this raw data, we can move it through Storm. We can create our spouts and our bolts, and then that brings us to our process data where then our apps and services can tap into it. Here's another depiction of how Apache Storm can be integrated within a big data environment. So this is now getting into the collection mechanism of running these transaction logs, if you will, or these commit logs. So we have a collector, which is collecting the information. Kafka is organizing the information. It is fed through Storm and then stored in either HBase or in our HDFS format. Then from there we can draw from our map producing techniques and work with the data. Well, thank you everyone for sticking with it. I know there was a ton of information that was just thrown your way. Hopefully, the content of this presentation should provide us with a general understanding on how to apply some of these big data concepts in tandem with each other. That was the goal of the presentation. Even though we got into some technical aspects, we need to be able to take a step back and look at it from 10,000 feet above and understand, okay, well, what is it really doing? To showcase this, let's take a look at the following chart provided by Microsoft. Hopefully this chart makes a little more sense to us now. So we can think of the information being generated by various devices. So it can be an application on the web, it can be a mobile phone or a mobile app, it could be sensors, web, social media, basically the entire Internet of Things, if you will. So we collect the information through APIs and various mechanisms. Then it goes into a queuing system, which is our Kafka process. Then the data can be pushed through quickly through Apache Storm. Then we store the information in an HBase system. And then from the HBase system, then we can query it using Hive or Pig, or move it into a data warehouse through Scoop, however we want, and we can move it to the presentation layer, which is dashboards, analytics, or we can actually push it back to a device. Additionally, we should now be in a better position to evaluate different implementations of Hadoop ecosystems. Here's a 100% open source ecosystem provided by Hortonworks. So this is taken straight off of their website in terms of what they bring to the table, and I've spent a fair amount of my time working with Hortonworks. I like it very much so. So if you're just getting into big data and you want to have a good ecosystem to work from, Hortonworks is fantastic. But I do also want to say there are many other implementations out there, so feel free to explore and find the one that works best for you. But we can see here, just by looking at the ecosystem, that we have these various components that we had talked about, and we have an understanding of what HDFS is, Yarn, Hive, Zookeeper, Oozie, Pig, so on and so forth. So this should now make sense to you when engaging in a big data context. I personally feel that a key point when deciding what the right big data solution is for your organization is that we need to remember to focus on the types of problems that you will be needing to solve. Do you need high storage capabilities? Okay, well, if I need high storage and I have big volumes of data, then I'm going to need Hadoop, HDFS, Pig, Hive, HBase, Scoop, and Oozie, to manage, how I work with this data. If I need real-time processing, okay, well, then I'm going to have to look at Kafka and Storm. Or perhaps I need both. Not only do I need real-time processing, I have to store this data, and that changes the framework of what you need. In any case, I feel that this tutorial should provide us with a strong enough framework for making a high-level assessment for big data needs. As data science professionals, our business leaders are going to be relying on us to lead the analytical direction of the organization. And if they want to get into big data, we have to be able to understand and speak about it intelligently. We don't necessarily have to implement it, but you should know, what the various components are doing and how they fit together. While concluding this part of the presentation, I just want to throw out some final thoughts on big data. The quintessential aspect of big data is not the data itself. It's the ability to discover useful information hidden in the data. Big data is not just Hadoop. Solutions may use traditional data management systems such as relational databases and other types of data stores. It's really all about the analytics that a big data solution can empower. Therefore, the data scientists are the people who will drive the intelligence that big data has to offer and will continue to grow the technology's adoption. So it's up to us, what we can do with the data, how we envision working the data to solve more creative types of problems are ultimately going to help drive the big data movement. So the technologies just enable the analytics. It's up to us to figure out, what type of intelligence we can gain out of it. Final note, good luck with your data science efforts and keep moving forward. Now that we've talked about big data technologies and gone into the ecosystem and the stack and discussed exactly how these pieces are working, I want to shift focus and get into some more R-related topics, because as data science professionals, this is a very significant tool that we use for machine learning and predictive analytics. Let's now approach working with the data from the R programming language. Here are some packages which are useful when working with big data. So if I'm working with HDFS, the R package I'm going to be using is RHDFS. If I want to do MapReduce, then I'm going to use RMR2. And if I want to work with HBase or Hive, I'm going to use RHBase. Note, these packages may have to be uploaded from the GitHub repository as they're not currently accessible via CRAN. So you might have to do a Google search to find the repository where they're housed, but installing them and using them are fairly straightforward, and they have really fantastic documentation. The first technique, which we will discuss in R, will be the MapReduce. This is the fundamental technique of working with big data, so we'll get into it. And we'll discuss it very broadly here, and then we'll pull it together in our practical example. Okay, so this is just giving just generic frameworks to work from. Okay, so if it doesn't make sense, don't worry, the tutorial and the practical example will really kind of fortify it. As data scientists, we do not need to think too much about the inner mechanics of the technique, as the implementation detail is hidden within the library. We don't need to know all of the IT underpinnings. It's a good thing to understand. Me personally, I like to know the mechanics of the systems that I'm working with, but you don't have to. And remember that this MapReduce technique is generic, and we can implement the technique to solve the problem at hand. So once we get our code down once, we can use it for different types of problems. The mechanism is going to be exactly the same. It's generic. The RMR2 package allows you to write R code in the mapper and reducer. This is great for those of us who don't know how to write code in Java. There's so much demands being put on data science professionals. You have to have a business acumen, you have to have statistics knowledge, you have to know how to work with data, work with technologies. Knowing every single language to write in is really quite difficult. Sometimes you have to sacrifice, one for the other. And in this case, we might not be Java developers, but we might be good with R. So what I like about this is we don't have to touch Java. We can just work in R. So here's some pseudocode in R for a MapReduce function. Okay, so remember we have to create a mapper, and then we have to create a reducer. So the first step of it is in the mapper, and then the second step is in the reducer. Okay, so we have our key, our value, and then we have our key prime and our value prime. Okay, so in the reducer, all the v primes with the same k primes are processed together, and so on and so forth. After we do this, we pass these functions to MapReduce. Okay, so we build our mapper, which is just a function in R. We build our reducer, which is a function in R, and then we pass these functions into MapReduce, okay, where we specify the map is our mapper in this case, and our reduce is our reducer. We can give it our own names, we can change it up, but in the most generic sense, this is what's going on. A nice feature of the RMR2 package is that we can test our MapReduce jobs on a local PC rather than through the HDFS architecture. This allows us to be able to test code efficiently and then move into the big data platform. So through the RMR options, we can specify the backend being local, and then that allows us to implement it directly in R. And we use this for development, testing, and debugging. I don't know if you saw the meme that I had earlier about the guy sending a bad MapReduce job that took forever to run and cost tens of thousands of dollars. Well, this avoids this. You can test your code, you can see the results, you can make sure it's working correctly, then you can pass it over to your Hadoop cluster. Likewise, if we want to push it to the Hadoop backend, we just specify Hadoop in this case. In a production Hadoop context, your data will be ingested into data frames by dedicated tools. We'll use Scoop in this case. For easy testing and development, the RMR2 package has two convenient functions that allow you to import-export a big data object into the R session. Again, a big data object is just the results of the data frame that you're working with, and you can move this into R. So here are the functions. We can use a to DFS or from DFS. Okay, and DFS just represents the data frames. Let's now take a look at an example on how to apply the MapReduce technique and get the data to work with. So here's what we need to do in R. We need to specify the input, map, and reduce functions. Optionally, we specify the output to persist the result in HDFS. If output is equal to null, then MapReduce returns a temporary big data object. A big data object is a pointer to a temporary file in DFS. So when we're setting our MapReduce context, we just need to understand when we're working with the output function, do we specify it as null or do we put it somewhere? If you know that the resulting object is small, use 2.dfs to return data from DFS into your R session. Okay, so in this case, we're defining our function. We have our m pointing to our MapReduce function, and then we invoke from.dfs, referring back to the m to bring it available into our R session. We need to remember that everything in Hadoop uses a key-value pair. This is a critical concept of it. So we use keyval to create the key-value pair inside your mapper and reducer. So this is breaking down these mapper and reducer functions. Use the helper functions, keys, and values to separate components from the big data object. So here is a cheat sheet for a MapReduce flow using RMR2. So we get a sample of data to DFS. We write our MapReduce function. So in this case, the function is map.fun. Then we write our function. We have our reduce function. We write our function, and then we bring it together in a MapReduce context. And in this case, we then inspect the results using our from.dfs. And then we can look at our keys and our value components. So this is a good section to refer back to if you want to see the specific R code. Well, now let's dive into a practical example. So we've talked a lot of theory in terms of big data processing. I want to show you exactly how you can do big data in R. The following big data example was presented at the Use R conference in Aalborg, Denmark in July 2015. The basis of the work was related to information made publicly available related to New York taxi services. The data set is quite large. Okay, it's about 200 gigabytes in an uncompressed CSV, and it's stored in HDFS. So this is a big chunk of data. I mean, it's not quite a terabyte or a petabyte amount of information, but I think it drives the point of how to work with the technology. Okay, so it really is big data. The data set contains information about every single taxi trip in New York over a 4-year period. So if you got into a taxi cab in New York, it was recorded using the little box that you see up on the dashboard, where they collect certain type of information, and then this information is stored. And now we are able to use it for data analytics. Our goal is going to be to bring in the data from HDFS into R, and then we're going to run a simple analysis using big data techniques. So we're going to employ different types of big data techniques in order to get us to our analysis. So the data is available at the following link on the top. For demonstration purposes, we'll be utilizing a sample of the full data set. So rather than getting into the whole 200 gigabytes of this, we're just going to create some sample files of some of the data. So on the right-hand side, you can see we have various sample CSV files, and if I open up each file in Excel, they're just CSV files. I see a data structure that looks just like this. Okay. And if you want to look at some of the analytics and related to this data set, you can check out the following resource from Brian Donovan and Daniel Work. Okay, it's really some very interesting insights. Here is the data definition of the various fields of the New York taxi data. So all of the fields, what do they mean? We have, the vendor ID. We have what time they were picked off, when they were dropped off, how many people were in the car, how long were they in the car, how far did they go, and we have GPS coordinates. So where they were picked up and where they were dropped off. So it is possible, to incorporate, some spatial analytics components, with this data set. So this is really a cool data set to play around with, and it's fantastic that it's publicly available. And a key point is that the columns in the individual CSV files do not have descriptive headers, which we will address later. So when we looked at that data set on the previous slide, we just had raw data in there. We will first set up a local instance within the RMR2 package. Okay, so we're going to invoke RMR2 in R, and then we're going to set our backend to be local in this case. And when you run this, it just says null, which to me is not very descriptive of what's going on, but just set the options, and that way you're working on the backend. The function make input format allows you to specify the attributes of your input data. The argument format CSV specifies a CSV file. This is a wrapper around read.table. So we're creating taxi format, we're using our make input format, we're specifying CSV, and we're bringing all the formats into a common wrapper. We use from.dfs to get a small file from DFS to local memory. So this is how we basically are pulling in the information through the from.dfs. And when we run this, we see, okay, here's our small example of a single trip data. It has 14,000 observations and just various information related to the data set or data frame. We will use keys and values to extract the components utilizing the from.dfs command. So when I take the head of the values, in this case, we can see that I have generic column headers, if you will, and I just have some values related to each one of the columns, if you will. Okay, but no descriptive headers right now. Well, why do the columns not have any labels? Remember, HDFS splits the individual files across nodes. So when we talked about HDFS and how it stores the data, we discussed this in detail. The implications are as follows. The chunk that's available to your mapper may not have a header file. Therefore, CSV files should not have a header at all. So when you're storing data into an HDFS store and you're invoking big data techniques, don't put headers on your CSV files. Okay, call it in at a later point, which we'll show you. And the solution to this is that we'll make a custom input format and we'll specify the column names. And we do this in kind of the same way you specify column names to your read table. So for those familiar with our syntax, this is essentially the technique that we're going to utilize. And we'll get into that. Fortunately for us, one of the files that we have to work with contains the data dictionary, and we'll need to use this to make an input format. So if I bring in this data dictionary, if you will, it gives me the following pieces of information. Okay, so it's just, a column description and the data type. So, medallion and integer. Then we can, through some R code, we can establish, the classes, and we can look at some of the header info. We use this data dictionary information to configure the input format. So now we're using our make input format. Okay, we're bringing our data in from the CSV, and we're bringing the data dictionary information to complete the input format. So now when we look at this, we get our output code, okay, that just kind of shows us, what the values are. In order to showcase the big data techniques in R, we will start off by performing a simple MapReduce job and then add more complexity later. The very first thing that we will do is we'll execute a basic MapReduce job without any transformation. So here is a simple MapReduce job. Okay, we have our input format, taxi format, we run it. It doesn't really do anything. Let's take a look at some of the values of the data frame. So here's the data frame that we've created now, and we can just look at some of the values, just get a feel for the data that we're working with. And this is something that I always like to do. Let's expand on this job and build in a simple query parameter. This technique is mapping in the 6th column of our data frame, which is the pickup underscore date time. So pay close attention to what we're doing here, because we're going to build off this concept. So remember, we're building our mapper function. So we're calling this taxi.map, and it's just a function. We have our key value store, and we're specifying in this case to take the 6th column. Okay, and that's what we're binding to our, the term original here. So then once we have our mapper put into place, we invoke it, okay, using our MapReduce function, and we can look at some of the data. So when we run the head values from .dfs of m, we see that we're actually grabbing header information related to the 6th column. Okay, and to show you exactly what we're doing, I think visually it's important, and we're going to show it graphically what we had just done. So in this case, we have HDFS, which has information, just being stored, related to the date. We have Tuesday, Monday, maybe sitting on one data node, Monday sitting on another, and so on. Well, our map function that we had just created basically is mapping the input of the 6th column, and it's just bringing the output of the map function is just a count of how many maps that we have. So there is no reducing component, and then finally what we're produced with at the end is just an aggregate count total. And if you look very closely, if you look at the 3rd box from the top, you see the output of the map shows Monday 1, and then all the way on the HDFS side, we see the count of Monday. We see Monday 1, recurring. So in the simplest sense, this is just what the code that we had just performed had done. Now here is a technique which incorporates the reducer function. So we built a map function, okay, and now we're going to also incorporate the reduce function. So as you can see now, we have a taxi.reduce function, and we have our key val now looking at the sum of v. Okay, and that's an important piece because that's the reduction. And then if you look at the MapReduce code that we have here, not only do we have our map being put in as taxi.map, we have our reduce equaling taxi.reduce. And then if we run the same header information using our from.dfs.m, we find that we have information related to specific dates readily available to us. Now notice that the taxi.reduce component contains that sum v, which I had alluded to, and that is a sum of the count of key val for a weekday. Okay, so when we run that final head values from .dfs, we actually get the total aggregate total down below. So graphically, let's look at what we had just performed. So here is the technique which incorporated the reducer function. So just like before, we didn't change anything on the mapper. side of it, we now have the reducer component. And when we do the reducer, we're taking from our mapping and we're inputting into the reducer and then aggregating it down to a smaller set. So look at the third box of the map from the top. So we have our Monday pieces. Notice how that shifts over in the reduce stage where we now have all the Monday pieces being brought together. This is that shuffling piece that we had talked about earlier in the map reduce. The input of the map reduce is just Monday 1, Monday 1, Monday 1, and then the sum of the V basically is, you know, doing a group by that date. It's now saying there are 3 Mondays. And then finally, the output of this reduce stage is then shifted, you know, back to HDFS in this case. Okay, so this is visually what was going on with the code from before, and I hope this really helps to kind of fortify, you know, what that map reduce process actually is working and what it is accomplishing. Notice the aggregation of the Monday count in the mapping and reducing output step. The question that we have is, can we write a better mapper and reducer that's more efficient in the processing? So if I'm looking at the Mondays in red here, we see that in the map stage, we have it reduced, you know, from Monday 2, it gets the output of the map gets shifted over as an input into the reduce stage, okay, where we have the Monday 2, Monday 1 down to Monday 3, and then pushing it all the way to HDFS. But is this an efficient design? You know, maybe we can do some aggregation at the map stage to improve the performance. And if we have really very large volumes of data, we need to be able to do this. Okay, so let's see what we can do to just be a little more efficient in our processing. We don't always have to do this, but if we're trying to optimize our map reduce jobs, this might be one way to do it. So here's how we execute that technique with a more effective mapper. Okay, so pay close attention to the code that we have here. Notice that we have an aggregate function within the mapper itself. Okay, and we see this statement right here. Okay, and by incorporating that in the map component, we're doing some pre-aggregation before the data is pushed into the reduce stage. And of course, we can invoke values, you know, from DFS of M, and we can get a count of our values. So now let's put it all together now. Okay, so we're going to do our map with some pre-aggregation at the mapping stage. Then we're going to create our reduce stage, and then we'll bring our map reduce technique together, and then we'll look at the information in total. Okay. So now we see for a particular weekday, so Friday we know we have, you know, 2,080 trips, Monday 1,689, so on and so forth. Well, let's now analyze the taxi data by the hour. Okay, so right now, you know, we were just looking at overall by day, but we of course, you know, can break this down into more granular levels. So likewise, we're going to write our map and reduce function. Okay, then we write our map reduce function that combines our mapper and our reducer. And we see by hour we have the number of trips. And of course, once we have this, then we're in a very comfortable zone because we can bring this in as a data frame into R, and we can perform all of our machine learning and predictive analytics and statistical tools. In this case, we're not going to do anything crazy here. We're just going to plot it in ggplot2. Okay, so we're going to, using the code on the bottom right-hand side here, we're pulling in the data, and we're just showing visually, where the peaks of trips occur and at what hour. So this simple chart here, shows some interesting analytics that are pulled in a big data context. Okay, so to me it's fantastic because we're taking data sitting in HDFS, we're bringing it in, building our own MapReduce functions, and then from the output of the function, then we're working on it through the R interface. This is big data at its finest. This section will show you how to get the output results back into the HDFS file structure utilizing the R-HDFS package in R. So here's an overview of different functions in the R-HDFS package. Of course, there's many things that you can do. If you go to the Vignette that's available and look at, all the different functions that are put within, but you can manipulate files in the HDFS file structure directly through R. That's the key takeaway here. So here's how we put the data from our local file system back into HDFS. So we've built our MapReduce function, we have our output, and we want to now take the data and we want to dump it back into HDFS. Well, we invoke the following code. Once we've tested our script in the local context, it's generally very easy to deploy on all of our data. So we've been testing it using our backend of local. Now we're going to actually move this into production. So we're going to switch from local and we're going to now change the backend to Hadoop. So when I execute this MapReduce job, this is what we see in terms of the execution. And a lot of it is a lot of techno-babble. Okay, it shows you, where the process of the map and reduce is at. But in general, this is the output that I would expect to see. The final aspect we will address in this tutorial will pertain to utilizing the Hive query language, or HiveQL, within R. Here are some key considerations when working with R and Hive. Remember, Hive allows us to define group by queries using SQL-like code. HiveQL translates into MapReduce jobs, and the underlying code is not displayed. So we write this HiveQL query, and it will perform the MapReduce jobs directly for us. Now, in order to do this, we have certain tools in R for string manipulation that allows for us to easily build complex queries. And we'll get into some of these tools when we're writing our SQL queries in the next slide. The package rhive allows us to run Hive queries directly from R. So it's a nice interface between R and Hive. And for more complex queries, we still need to use other tools like RMR2. So if you want to write the complex MapReduce functions directly, use RMR2. But if you want to write in Hive, or using a HiveQL, we can invoke rhive. Specifically, what we will focus on is we'll build queries using string manipulation tools like sprintf and paste. Okay, so those of us who are familiar with the R ecosystem, these are very common techniques to use. And we're going to run some queries using rhive. There is a syntax difference that we need to remember when writing queries in Hive versus writing Hive queries within the R interface. Okay, so for those who are more programming focused in their work, just remember when we're working with R and Hive, it's slightly different than working in Hive directly. Okay, but it's really quite simple. In Hive, you put a semicolon in the end. So for our SAS users, we're quite familiar, with the semicolon. Okay, I'm sure if you talk to any SAS programmer out there, that'll be the bane of their existence is the semicolon. In our Hive, we don't have to deal with this. There is no semicolon in the end of the statement. Okay, so that's one of the key differences when working with HiveQL between the two formats. Using Hive, we can replicate the RMR2 example, counting the number of taxi runs by hour. The steps are as follows. We're going to import the data, and we're going to query the data. Starting from our raw data, we can create a Hive table. Since the data is already in CSV format, the easiest option is creating an external table. What we need to specify in order to do this is the data's location, the data format, and the field formats. So here is the full Hive query to create an external table. So if I'm working in Hive, on my HDFS, this is the syntax that I would write. Okay, and we're going to break this down into pieces. So there's a lot of information in here. Okay, but just understand that this is the syntax that we need to put. Now, just by looking at the data, notice the similarities to the SQL language. If you're comfortable writing queries in SQL, or for our users, SQLDF, the learning curve for Hive will be lessened. So let's now go ahead and focus on breaking down this query into its constituents. The first part of the query defines a table called taxi sample and the format of its fields. Okay, that's very straightforward. Anybody who's done a make table query in SQL, is familiar, with exactly what we're doing here. Straightforward. This part of the query defines the data format. And then this part of the query defines the HDFS path to the data folder. Now that we've reviewed the basics of a Hive query, let's set up our Hive. Okay, so we're going to invoke the library. Okay, we're going to establish our directory, and we're going to do some basic initialization procedures, such as where the host is located and connect to the Hive. Okay, so please see the documentation to make sure that you're setting it up correctly on your stack. But for now, this is what we need to do. So here is a simple Hive query in R to count the number of records. Okay, so we're not going to do anything crazy here. We're just going to count how many records are in this database. So now notice in this case, we're establishing the query count. Okay, it's got our SQL type syntax put underneath the quotes, and then we create our table count using our Hive query, and then referring back to our query count. In this case, and when we take the header of this, we get our count total as shown below. Here is a string manipulation technique for writing the same query utilizing sprintf. So notice the syntax, it's a little different in this case, but we can see that we can reconstruct our count in this case. And so, like most things in R, there's more than one way to get us to the same answer, and we're just showing a couple different techniques that you could utilize. So use whatever you're most comfortable with. Now that we have an understanding of the basic mechanisms of a Hive query within R, let's recreate the count example we originally built using MapReduce and the RMR2 package. So we're going to figure out how to query the hour. So we've created our HiveQL syntax in this case. And if we want to do it in sprintf, this is how we do it. And remember, the Hive query syntax in this example is as follows. Okay, now we're setting the limit of 100. In this case, in production, we wouldn't actually set the limit here, but we're just trying to showcase the example. So now that we have our query syntax developed, we can execute the Hive query. So when we execute the Hive query, this is what we give us. we have the date time, and we have the hour associated with this. So the results of this Hive query gives us the hour associated with each pickup date frame entry. So this is that 6th column that we were looking at from earlier. We can now build off of the query in order to create an aggregate count by hour. So this is just showing, just what hour was associated to what record, but it didn't actually give us a count in this case. So we have to build a more formal SQL statement. So we're going to have to put a group by in this case, and we're going to have to do a count, or we can use other aggregate functions if we want. So we're not looking for sums; we're just looking at counts. And if we want to do it in sprintf, this is how we would do it. And from before, here's the query syntax that we would use for our Hive query. Finally, we have the query syntax developed, and we can execute the Hive query. So when we execute the Hive query, this is the result that we get in this case. So as you can see, we now clearly have by hour a summation of the total count. Okay, and the results of this Hive query gives us that aggregate count of each hour associated with each pickup date time entry. In this big data example on the New York taxi cab data, we developed scripts in R with the RMR2 package. We constructed mappers, we constructed reducers, and we deployed MapReduce functions. As a matter of fact, we even optimized our MapReduce function by creating aggregates in the mapper stage. Then we returned the data to our local R session and plotted the results with ggplot2. Now, of course, we can transfer this to a data frame and run different types of analytics and draw from our entire suite of tools, but we just showcased that once we have the data, we can do what we want with it. We also showed how to upload files into HDFS using RHDFS. Afterwards, we turned on Hadoop from our local installation, so from our test environment to our production, if you will, and we ran the script directly in Hadoop using the Hadoop context. Finally, we constructed the same example as before utilizing Hive through the rhive package. This practical example showcases how we can integrate our data science techniques in R within a big data ecosystem. So hopefully when you look back at this tutorial and you're thinking, okay, well, how do I do big data with R? You can go back to this example, and this will kind of shed some light on the techniques that you need to use in order to make it happen. Thank you very much for joining this tutorial. I know this was a very intense one, and I tried to be as concise as possible. I mean, it's clocking in at about 2 hours and 50 minutes, but I appreciate you taking the time. Go back to this one, check it out, and if anything is unclear or if you have any questions, please feel free to reach out to me directly. Thank you very much.